We were talking last time, the last thing we did was talk about polynomous logistic regression, and that's dealing with a situation where the outcome variable, if you're doing, particularly doing logistic regression, but the outcome variable has more than two categories. And in particular, the outcome variable has more than two categories, which are separate categories, and they're sort of they represent a categorical variable which doesn't necessarily have a clear-cut ordering. You can't say the three categories are none, mild, and severe. They're different categories. So when you're dealing with three or more categories, and that's your outcome, and you have an exposure or more than one exposure, and you have variables you want to control for, you want to consider interaction, then the traditional approach to that is polynomous logistic regression, and then we're going to then talk for most of the time today on ordinal logistic regression. Okay, so when we talked about polynomous logistic regression, I had an example where the outcome variable was cause of end-stage renal disease, and there were three possible causes: hypertension, diabetes, or other. And the question was whether race was related to what the cause was. And there were two control variables. These are people who had end-stage renal disease. They were undergoing dialysis. And the two variables identified for control were age at dialysis initiation and gender, okay? And so when I talked about this example, I said, well, one way, if you, in this particular case, is just three categories of the outcome. They're not orderable, and the simplest way to describe the data is in a 3x2 table, three categories of the outcome. And if you're only dealing with the crude effect and you're not controlling for anything, and the exposure variable is race, black or white, then the simplest way to describe the analysis is in a 3x2 table. And when you're doing that, what you're going to wind up doing is computing odds ratios related to the table. And if there are three categories of the outcome, there'll be two odds ratios. If there's five categories of the outcome, there'll be four odds ratios, right? That's what we talked about. And the odds ratios, in order to get them, you have to decide on a referent group, and then you compare each of the other two groups with the referent group and compute the odds ratios. So in this case, I get three odds ratios, but the last one is 1, because that's the referent group with itself. And this says hypertension with others, 2.105, and diabetes versus other is 1.484. And that's the simplest way to describe that, that kind of data if you're not controlling for anything. And actually, even the crude data, well, this is an example of the crude data for this case, the crude data can be put into a form of a model. You can write it in terms of even a simple form, a polynomous logistic model that only deals with the crude data. And in order to do that, basically what you have to do is write two equations that describe at least the two odds ratios that you're trying to estimate. Because you got these three categories, you're estimating two odds ratios. So one of them, one of the equations deals with the comparison of, this is diabetes versus other, and this is hypertension versus other. And you're getting two equations, and if you're only dealing with the race variable, not controlling for anything, this is what these two equations look like, and they combine to form the polynomous logistic regression model for this situation. Okay, if you want to control for age and gender, and you put age in 7 categories, then you're going to have 6 dummy variables for age and 1 variable for gender, adding that to the model, and then the model is a little bit more complex. And both of these models are no interaction models, because you can also have product terms involving the exposure and any of the variables you want to control for. But both these models are no interaction models, and I described how you would go about the process of fitting the model. You basically can use SAS to do that, SAS Logistic, and the key extra thing you have to do in the code, I talked about somewhere in here, was, well, I don't know where it is, I guess it was near the end, was you have to add this link equal to glogit to the code to tell the computer you're doing polynomous logistic regression. And then when you do that, it'll give you an output. And for example, we looked at output for this is the output for the model that controlled for age and gender, and looked at the effective race controlling for age and gender. And the output, there's a lot of stuff here, but the only coefficients of primary interest to you in this model, this is a no interaction model, are the two coefficients of the race variable, because that's your exposure variable. And there's two categories of race and three of the outcomes. So you get these two estimated coefficients, and in order to get the odds ratio that describes the effect of race on comparing hypertension with other or comparing diabetes with others, you take each of these estimates and you exponentiate it, e to the beta. And when you do that, you get a table of odds ratios. Now you notice there's a bunch of other things in the table because you've got other variables you're controlling for. But these variables you're not primarily interested in, particularly in this case because there's no interaction. You would be some of these other variables, or particularly in this in the maximum likelihood estimates, you'd be interested in that because if you had interaction terms, but you don't have any. So the only two you're really interested in is the race variable. But you're getting two estimates for every other parameter that's in the model because you got two equations. Okay. But anyhow, that's what you do with this, and that's how the thing works. And in fact, that's where I sort of ended up, except that the one thing I didn't say, and these are the two odds ratios, 2.901, 1.776, and these are different from the crude odds ratios that we got for this data. We didn't control for anything because we're controlling for something, so they might change. That's what happens when you control for something. Okay, and they changed a little bit, but not a lot. Okay, so are you with me with this? That's what polynomous logistic regression is all about. And the thing I didn't show you was the general form of the model, the general form of the polynomous logistic regression model. And you could write it like this. I mean, some of you who might feel mathematically you're not that comfortable might look at this and start twitching a little bit. But this is the general formula for it. And basically what it says is the model you notice it says G equal to 1 to G minus 1. So that says if you have three categories that you're looking at of the outcome, then you're going to have G minus 1 equations to have to look at. And each equation is comparing one of the categories with the referent group. So this is the G category, and you have G goes from 1, little g, and little g goes from 1 to G minus 1. And so if like I have on this thing, if capital G, if you have three categories, then G minus 1 is 2, and you're going to have two equations to deal with. That's how it works. Okay. If G was 4, you'd have three equations to deal with. So that's the general formula, and this is just an example of the formula when G is equal to 3, similar to what we had in this example, but I only put in gender, I didn't put age in here, just as this illustration. So that's what the general formula looks like, and there's a general formula for the odds ratio. So the formula for the odds ratio is that if you have capital G, G could be 3, G could be 10 categories, then you're going to get several odds ratios, as we saw. Yes?
How does the coding for the outcome variable work? Because, I mean, normally when you do regular logistic regression,
yes.
Comparing a 2 and a 0, you would have to account for that when you exponentiate. So is that expecting that we're just coding?
Well, you have to code it the way, you have to tell the program what your reference group is. If you do that, then it's going to do it. And you say G, link equal G loads it, it'll use the right reference group and give you the output that corresponds to that. So that's what you have to do. Now, somewhere in here, I don't remember where I showed it again. Was it up here or later? It was after this. I just left it, I said descending. So that's telling you that the reference group is I guess that says the reference group is the highest one. No, the reference group is the lowest one, the 0, right? Which it was in this case. But if I wanted to have a specific one, I wanted a reference group to be 2, I might say model, and I'd say something like when I have the outcome variable specified, I specify the reference group to be something different. So that's what you have to do in the code. And this was the code. This is when you don't have any other variables you're controlling for, and this is when you control for them. Okay? So that's polynomous logistic regression. Okay? And you want to consider using that, again, if the outcome has more than 2 categories and it's not orderable. And this was an example of a situation like that. And I have another example of that situation dealing with times, well, there wasn't mammography. I can't remember what the example was. It was a different example from a different data set in the textbook, the logistic regression textbook, than this example that I'm using here. So there are a couple of different examples, and of course there are plenty of practice exercises, and then you're also going to have the practice exams to do. So, and then at the very last thing, I don't know whether I showed this, I think I mentioned it, is I showed you the code for ordinal logistic regression, and I just said a few things about it, but we're going to talk about this some more. The main point that I meant about this is an example that I'm going to describe where it comes from shortly, but this is an example where, again, it's proc logistic, and this is doing ordinal logistic regression, and the one thing you notice here that's different from what I wrote in these other statements, where it says link equal G logit, there's no link equal G logit in this statement, in the model statement, as it was here in the model at the end, / link equal G logit. You don't see that here, and the reason why is because this is a code to do ordinal logistic regression, which I'm going to now talk to you about, how that works. Okay? So why this code? Well, we have to look at the example and talk about what it's all about. Okay, so now I want to talk about ordinal logistic regression. So let's see if I can get my slides up here. It's not the one oh yeah, okay, that's the one at the end. But let's go to the beginning. Now, what did I do? Did I get rid of it, or? There you go, okay. Ordinal logistic regression, okay? That's what we're going to do now, until the end of the end of today, the end of time, I don't know, something like that. So I want to talk about now, there is a term, there's an example I want to talk about, and I'm not good at pronouncing this word. You want to help me? What does that say? Acinetobacter. Is that close? Acinetobacter? What is that? That's a bacteria. It's a bacteria that people get, particularly they get that when they're in hospitals. Okay? And if they get that and while they're in the hospital, they've undergone some surgery and they're getting this bacteria that as they're dealing with the surgery or trying to recover from the surgery, then you want to treat them with something, usually some kind of drug, that's going to get rid of that. But some people are resistant to that, resistant to the drug. So if they're resistant, we call them resistant to whatever the drug is. So this is a study that is dealing with drug resistance to treating Acinetobacter bacteria with patients with that. Okay, and so I'm going to talk about that. Okay, now, so what's an ordinal logistic regression? Start off. It's an extension of binary logistic regression to allow for ordinal outcome variables. So the outcome variable is no longer just categorical where you can't order them. Somehow you can come up with an ordering of the outcome. Okay. Now, it turns out there's a number of different kinds, or a number of different ways to do it, a number of different models to deal with ordinal logistic regression. And the most popular of these models is called the proportional odds model, which is what I'm going to talk about today. And there's another name for it. It's called the cumulative logit model. There's 2 alternative terms that describe it, but it's called the proportional odds model. One thing I have to do today is talk about what do I mean by proportional odds? Well, where does that come from? Where does that term come from? Okay, but there are other types of ordinal logistic models, and it's been written in various papers and stuff, and there is a paper that I was involved in about, 1997. That was a few years ago, not as long as I've been around, but I keep hitting something, and it's great. But anyhow, there were other procedures, but the reason why I'm talking about the proportional odds model is because the SAS proc logistic, that code that I showed you, only does the proportional odds model. It doesn't do any of the other models. And so if you have a situation where you need to use one of these other alternatives, you're going to have to go to the literature, a paper like this that I've mentioned, and I think I've referenced, I've referenced sort of, roughly, what the papers, I've certainly referenced it in the chapter on this, and not only my paper, but another paper that was written about that, and there are other papers in that chapter. But if you have to go to some of these other references if you want to do something different, because it's not available in proc logistic. Now, another way to say that is that if you're going to use SAS to do this ordinal logistic regression, then you have to be convinced, or you have to be satisfied that you can use this model, the proportional odds model. Okay? If you can't use that model, then you have to use something else. Now, there is a way, and I'll be talking about this as I go along here, how to check whether your model is appropriate to use SAS. And that involves doing some kind of a test, and it's called the score test. So we have to talk about the score test and what that means. And if you do the score test, the null hypothesis is that the model that you're using, this ordinal logistic model, proportional odds model, satisfies the proportional odds assumption, so you can use it. That's the null hypothesis. So if you reject the null hypothesis, this null hypothesis that the model is appropriate, then that means you got to be careful. You shouldn't necessarily use this model. You have to do something else. Although maybe you can finagle around and try to figure out, justify it some way, which I'm going to sort of talk about a little bit through this example. Okay, so again, we talk about ordinal variables, and there are different kinds of ordinal variables, but they have a natural ordering at its different levels. You can talk about cancer tumor grade being well differentiated, moderately differentiated, to poorly differentiated. You can talk about the outcome could be length of hospital stay, how long they're staying in the hospital, short, intermediate, long. In fact, that's the example, the Acinetobacter example I'm going to be talking about here, where this was the outcome. The outcome was how long they stayed in the hospital, and it's going to be an ordinal outcome. And there were three categories: short, intermediate, and long. Okay. And there could be others, and this is the example used in the chapter on ordinal logistic regression in the logistic regression book that you have, where the outcome is time since previous mammography, which would be never had one, within 1 year, or greater than 1 year. Okay, so that's another ordinal outcome. So when you have an ordinal outcome, the first thing you should think about, if it's more than two categories, then you should think about using ordinal logistic regression. That doesn't mean you couldn't also use polynomous logistic regression, but if you do, you're not sort of taking into account the ordering, and you might lose something in terms of getting precision or power in the tests that you're doing, or in the estimates that you're getting, if you don't take into account the ordering. So that's why you want to use ordinal logistic regression if you have an ordinal outcome. You also want to use it if you have an ordinal outcome and you're using a proportional odds assumption and you decide it's satisfied. Now, if it turns out the proportional odds assumption is not satisfied, so you can't use proc logistic and SAS, one of your alternatives is to use one of these other methods that I listed on the previous slide. Another alternative is to do polynomous logistic regression. And you're doing something different if you do that. You're not taking into account the ordering, but at least you're doing something. Okay? So that's something else you can do, but it's better to do one of the other outcomes, but you can do polynomous logistic regression using SAS, at least, using proc logistic. Okay, so there are some of the references, okay. Now, this is the little background about this bacteria, and basically it's something that's difficult to treat due to the emergence of strains of resistant to almost commonly prescribed to many different kinds of antimicrobial agents. There were outbreaks, and it's been a problem, particularly, I said, in military medical facilities, I said at the bottom of the screen here. But in any case, I want to talk about this study, okay? And this was a study that when I've been working at CDC in the what's now called the Division of Health Quality Promotion. It used to be called Hospital Infection Control. So you can imagine relates to this thing. For quite a number of years now, maybe 10 years, I spend 1 day a week there. They pay part of my salary, okay? So to the first, almost the first year that I was there, this one of the EIS officers that was there came up to me and said, I got this problem. And her name was Rebecca Sonnenschein. So what a great name, right? Sonnenschein, Winter, I don't know, but Sonnenschein, that was her name. So, and I don't think she changed the name. I think that, I'm never sure. But she was a lovely person. Spent a lot of time working with this study, with her on this thing, and some other people at CDC. And what it was, as I said, it was a retrospective matched pair cohort study. Not a matched case control study, matched pair cohort study. So people were followed over time. And these were people in the hospital, and they were followed over time to see a number of things. There were 3 outcomes, in fact. One was whether they died, in-hospital mortality. I said mortality, but I meant mortality, okay? Length of hospital stay, that's the one I'm going to illustrate here. How long they stayed in the hospital. And another one was length of stay in the ICDU, but I'm going to talk about the length of stay generally in the hospital. So that's our focus. And it used patient records in 2 hospitals in Baltimore to deal with this data. We'll look at how many people were involved in a minute. And then the question of interest was whether people, see, some of these people who got this infection, some of these people got an infection that was resistant to treatment. And some of them had an infection that was not resistant to treatment, could be treated. Okay, so we would call that susceptible to treatment. And some of them even didn't have, there were 2, the exposed group were patients who were resistant. There were 2 unexposed groups. One was patients who were susceptible, and another were patients who didn't have the infection. Well, I'm going to focus on part of their study. I'm just going to look at the comparison of exposed with unexposed group 1 to talk about to what extent exposure status was related to how long they stayed in the hospital. You might expect that somebody who was resistant to infection had to be treated somehow to get rid of the infection, and they had more of a problem than just recovering from surgery, whatever they had. We're going to stay longer. Well, did they really stay longer? That was a question, compared to people that could be treated. Got it? That's the issue. Okay. And, well, they matched. Okay. Now, that's another. So, in any case, we'll talk about the matching in a second, and it's a cohort study. So they had people who came to the hospital, and actually, as I said here, 56 matched pairs. So there was like 112 people, right? 56 of them were resistant. Another 56 of them were susceptible, okay? And they followed each of these 112 people as they went through their hospital experience until following how long they stayed in the hospital. So that's the outcome variable that I'm focusing on, okay? I am going to describe, I've used the term AC status to define the exposure variable. 1 if exposed, 0 if unexposed. Exposed means resistant, unexposed means susceptible. So I don't have to say Acinetobacter every time. I can just say AC status, and it saves me messing up on my pronunciation, but I'll probably mess it up anyhow. So, And the outcome variable was ordinal hospital stays, defined from terciles of hospital length of stay using three categories. It was defined, the outcome variable was defined into three categories. Now, if you think about hospital stay, length of hospital stay, it could be 1 day, 2 day, 3 day, 4 days. So it could be, considered to be like a continuous variable, length of stay over time. How long did they stay in the hospital? Okay. And if you think of that as the outcome, just time in the hospital, what kind of a model would you think you'd want to fit to this if you want to look at the relationship between exposure and this outcome that was time treated continuously? What kind of a model? A linear model. Very good. Did that well. Okay. Very good. A linear model. Okay. Now, turns out that a linear regression model could not be used for analysis because the original outcome variable, hospital days, was not normally distributed, even when log transformed. So they tried to do linear regression. It didn't work. That's what I'm saying. So they said, I still want to do something, and I want the outcome variable to be length of stay in the hospital. So in order to consider the ordinal natures, because this variable is ordinal, the use of an ordinal logistic regression model was considered, and then they had to figure out, well, okay, what are the ordinal categories and how many categories? And they wound up looking at it a number of different ways. They came up with 3. 0 if the number of hospital days was between 0 and 9, and 1 if it was more than 9 and less than or equal to 23, and 0, 1, or 2. Those are the 3 ordinal values these are the 3 categories, these are the 3 ordinal categories, and they said 0, 1, 2, but 0, 1, 2, those values are ordered, right? Because 1 means they stayed longer than 0, and 2 means they stayed longer than 1. So the outcome variable is an ordered outcome variable, okay? So, they had to make some other decision about patients who died in the hospital, and they excluded them from the study. That could be discussed, but I'm not going to get into that because it was reasonable, but anyhow. So let's talk about the matching part, okay? So they did this matching, okay? They had people who were exposed, and they matched them on people who were susceptible. They chose susceptible patients who were somehow had something in common with the people who were resistant. And what they did was they said, this is how they defined it. A susceptible reference patient had to have a pre-infection length of stay within 5% of the matched resistant Acinetobacter patient's pre-infection hospital stay. So what they did was they said, we're going to match people, we're going to take a susceptible person who stayed in the hospital, who was in the hospital prior to getting the infection, as long as about the same amount of time as the people who were resistant. So they're having a sort of an equal amount of exposure in some sense to when they got the infection. That's the idea for matches. So it's a matching variable, okay? So now when you start thinking about matching, well, then you start thinking about, well, what did we talk about? We talked about logistic regression. And now the outcome variable it's not binary, it's ordinal, okay? And we're talking about match data, okay? Now, what we learned about match data, and we learned about it only in terms of a binary outcome. We didn't talk about it ordinal, because now we're talking about it. What we learned is if you want to consider an analysis of match data, and what you did was you had a model, a logistic model, whether it was even for binary, you had to put some dummy variables for the matching. Remember that? Dummy variables for the matching. Okay. So if there were 56 matched pairs, and you're even treating them as separate strata, you'd have to put in 55 dummy variables for the matching. If you did some kind of pooling, which talked about a little bit in the textbook in the matching chapter, you might still not reduce the number of strata that much. So the problem is, if you have a lot of matching strata, what procedure do you have to use? Conditional logistic regression, because that was the thing we talked about. If you use unconditional, you get a biased answer. Problem was, if you look at proc logistic in SAS, there's no way you can do matching for ordinal regression. There's no way you can do it. There's no conditional, turns out conditional thing is only in there if it's binary, not if it's a binary outcome. So, and I don't know if it's been changed since then, but when we were working on it, we couldn't do it. So we said, oh, wait a second, maybe, remember one thing we learned was that if the number of strata, or if we did some kind of pooling, if the number of strata involved in the matching was small, then maybe we could still do unconditional. That's what we did. That's what we did in order to make this so that we didn't have to worry about something that wasn't in SAS, and we could still do unconditional. So we're playing little games here, but that's what we're trying to do an analysis, okay? And so what we did is, rather than have 56 strata, we wound up having 56 matched strata. We had, 7 matched strata. Well, I guess it's 8 matched strata. And that's not 56, so that's a lot shorter. And we said, well, that justifies that we can maybe do unconditional logistic regression, which we could do with an ordinal outcome, and that's what we did, okay? So I'm just telling you, we did this matching. We didn't use conditional. We figured out a way to use unconditional because we couldn't have used conditional given what was available, and I think it's still not available. And then we also, so we're controlling for the matching variables by having this variable, new x time. X time stands for exposure time. And new x time has to do with the fact that we didn't use all 56 strata. We did something to shorten this, to shrink the number of strata. And then there were 2 other control variables, which were called Apache and Charlson. Apache was a measure of severity of illness prior to infection, and Charlson was a summary measure of comorbidities. These were 2 other variables you wanted to control for. It's like how sick were they? How serious were they? That was the idea. 2 other variables to control for. All of this, I think, made sense. So we were controlling for exposure time and these 2 variables, and the question was were people who were resistant more likely to stay in the hospital longer than people who weren't resistant, who were susceptible? That's the plan, okay? So you want to put things into that kind of a context, okay? So now here's the data, okay? Or here's the simple, crude, this is table A, the crude data from this data set. You notice it says 112 over here, okay? Okay, and I got everybody in here. I've got infected versus susceptible, and I've got the 3 categories of the outcome. And I got these 3 categories and whether they're infected. So there are 6 numbers in the table. It's a 3 times 2 categorical table. It's a 2 by 2 table, but it's a 3 times 2 2 by 2 table. Now, these data don't control for the matching, and they don't control for the Apache or Charlson. And again, an ordinal logistic regression model allowed for this control as long as we did what we did about the matching, keeping the number of matching categories to be small. Are you with me with this? I haven't done anything fancy. I haven't shown you what the model looks like. I haven't done it. I'm just telling you what the problem was. Okay, I don't know if you're with me on this, but this is the easy part. Right? So now, this is a little bit complicated in terms of this, but again, this is still easy if you think about it. Now, here's the table that I just showed you on the previous slide, and here are 2 other tables. Now, what have I done to get these 2 other tables? How have I gotten these 2 other tables? Well, you notice these are the numbers in the original one, and this is a 40 and a 36. How do you get the 40? I add the 24 and 16 to get the 40, and I add the 13 and the 23 to get 36. And then I keep the last 2, 16 and the 20. That's this table. Okay? And then I got this table, 24, 13. How did I get 24? Well, that's the first row here. Now, how did I get the bottom thing? 16 and 16 are 32, and 23 and 20 are 43. So that's how I got the bottom one. Okay? So what I've done is I've taken this 3 by 2 table and written it as 2 by 2 tables. That's what I've done. Okay. Now, what I did, you may notice, is that I'm comparing groups or outcomes 1 and 2 versus 0, 1 and 2 versus 0 for this table, and I'm comparing 2 versus 0, 1 for this table. That's what I'm doing to get these two tables. What didn't I do? Is there another table I could have formed? What didn't I do? 2 and 0 versus 1. I didn't do that. Why didn't I do that? It's what? It's not reasonable. Well, why isn't it reasonable? It's breaking up the ordinality. In other words, I'm keeping the ordinality by doing 1 and 2 versus 0, or 2 versus 0, 1, but 2 and 0 versus 1 isn't keeping the ordinality of the data. I don't want to do that. I don't want to have a table like that. So I only have these two tables. I don't have the other table. That's the only other choice I have. Okay? So now for these tables, I can compute the odds ratio for what's in the table. I get 1.39 and 2.48. That's what I get for these two tables. Now, what I wrote over here was that these two odds ratios should be approximately equal to justify using ordinal logistic regression with the proportional odds model. If you look at these two odds ratios, they should be about the same. Are they the same? Almost anybody looking at this is like, gee, they're really different. This doesn't look like I should be able to do this. Okay? But I did it anyhow. Okay? Because you might say, well, you can do anything you want. No, that's not why I did it. I had a reason for doing it. Okay? And the reason for doing it was that, you see, these two values, or these two tables, were obtained from the crude data. The crude data. All I did was consider I didn't consider exposure and disease. I didn't consider the variables I wanted to control. And there were 3 of them. Okay? So if I considered the crude data, and I considered what I would have to do in terms of tables, which is getting pretty complicated for the variables I wanted to control for, well, would that come out to be something that the odds ratios that I would have to compare, would they be very different, or would they be the same? Well, it turns out that the way I can deal with the control variables, and in a bigger model, because that's what I wanted to do. Wasn't just doing the crude analysis. The way I can do that is I can use this test procedure. And what's it called? I mentioned it. The score test, whatever that is. Well, it's a test that the computer will print out. As soon as you say, use the proportional odds model, and you write the code, that'll be something that gets printed out in your output. You'll get a test statistic, and you can test whether it's significant or not. It turns out when I actually, and which is sort of equivalent to looking at these two odds ratios, but you have more odds ratios because you're controlling you got a lot of tables you're dealing with. And what happened was when I did the score test, it was not significant. So the score test allowed me to justify using the proportional odds model, even though if the score test for this would be significant. But this is not the whole story. This is just dealing with the crude data. So I was able to justify using the proportional odds model when I considered all the variables I wanted to consider. Okay. Again, I'm not writing the model or anything. I'm just telling you what we had. Now, here's another table. The previous table was table A, and table B divided table A into 2 subtables, right? Now, here's a table C. Table A, table B, now I'm showing you table C, okay? Which is, as I said, a hypothetical example. This wasn't the data, but I'm saying suppose this was the data for these, for the 3 possible ordinal outcomes and the infected susceptible groups. Okay, suppose you did that, and I divided the data just like I did previously, but this is what I'd get. Notice that the odds ratio for each of these tables is 2 and 2.06, right? Very close, right? This would be the kind of situation, if only you were using the crude data, that you'd wind up saying, oh, I can use, I can use the proportional odds model to model the crude data. That's what justified, because you look at these things are essentially close. But I couldn't do it here unless I did something more, and I wound up doing something more complicated, but it was the score test when I considered all the variables I wanted to control for. Now, it's possible that if I considered all the variables I wanted to control for the hypothetical, this was just hypothetical, I didn't have the rest of the data, I didn't make up the rest of the data. If I had the rest of the variables, maybe when I used the score test, it would be significant, even though the score test for this was not significant. But I didn't do that. I'm just trying to show you what you'd like to see if you're just looking at the crude data. Okay. Are you there? We there? You know, I still haven't done the fancy stuff yet. This is the easy stuff. Okay? Okay, now, even this isn't that fancy because it's just a bunch of words that I'm going to talk about. The score test for the proportional odds model it's a test statistic. You get a test result. You get a value of a test statistic, and it's approximately chi-square, and it has degrees of freedom S times K minus 2, where S is the number of predictive variables in the model, and K is the number of ordinal categories of the outcome variable. Now, for our example, how many ordinal categories were there? 3. So what's K minus 2? 1, right? Now, for the crude data, what's S, the number of predictive variables? Just 1. Just had exposure, right? And whether you were resistant or infected or susceptible. So S is 1, K is 3, so it turns out that degrees of freedom is 1. The K, what is it? S times K minus 2 is 1. Okay? And I wound up doing the score test for that hypothetical data, just to show you what I didn't do it for the other one. I guess I should have, but I didn't do it. For the hypothetical data, this chi-square statistic, the chi-square value is 0.0082, and the p-value is 0.9281. What does that say? What's the null hypothesis? I'm doing the hypothetical data. The null hypothesis is that the proportional odds model is okay. That's what the null hypothesis is. And this says it's not significant, so it is okay. At least I can't reject it. Okay? That's what I get when I do that. Okay? Now, what about what we wanted to do? Okay? Now, if we want to consider AC status, or that's our E variable, binary, Apache, which is a continuous control variable, Charleston, another continuous one, and nu x time, a categorical variable with 7 dummy variables, dealing with the matching thing, then it turns out the chi-square was 8.7459, the degrees of freedom was 10, p-value was 0.5564, not significant. Now, where did I get degrees of freedom 10? Well, K is still 3, because the outcome, there's still 3 categories of the outcome. But what's S? S is the number of predictive variables in the model. Well, there's 1 for exposure, there's 1 for Apache, there's 1 for Charleston, that's 3, and how many for nu x time? 7. Okay? So that's why it was 10. Okay? And so even though when you looked at the unadjusted or the crude data, when you looked at what you were dealing with, you could say, I can use the proportional odds model, whatever that is. Again, I haven't shown you that, whatever it is, to do this, okay, to carry this out, okay. So I've done the score test, and that's what I've done, and you can do this. Now, here's what the model looks like. Well, this is one way to write the model when you only have a single exposure variable, and you're not putting any other, you're not controlling for anything else. The exposure variable is E. Here's the model. Now, this is a weird-looking model statement given what you've seen before, because, you know, the usual statement that you got for the logistic regression model was P of X was the probability that the outcome was equal to 1, given the variables that were predictors in the model. This doesn't say that. It's D, given the outcome was greater than or equal to G, and G is 1 or 2. Now, G is 1 or 2. Remember, there's 3 categories, 3 ordinal categories. When there's 3 ordinal categories, the maximum number you can have is 2. It's always 1 less than the number of ordinal categories. This little g is 2. And it turns out this model is written like this, and in this model, there's alpha sub g alpha sub g is either 1 or 2, depending on whether the g is 1 or 2. And for this model, the way it's stated is that alpha 1 has to be assumed to be greater than alpha 2. Somehow that's one of the assumptions of the model. Now that's weird, okay? So you got to deal with this a little. We got to deal with this a little bit, okay? Now one thing you notice in this model that's different from the polytomous logistic regression model is you notice that the intercept has a subscript, G, subscript G. But what about the beta, the regression coefficient? It's not beta sub G, right? It's just the beta. Now, if you remember in the polytomous logistic regression model, all the coefficients had a subscript depending upon which stratum we were talking about, or which category we were talking about. These things had subscripts, but there's no subscript here. That's what this model says. No, even though there's a subscript for the alpha, no subscript for the beta. So if you were looking at this model and you didn't hardly know this model is really confusing in some ways and all that, but you said, well, look, suppose I want to use this model to come up with a formula for the effective exposure. What would you think the formula would be? What would you think the formula, given like what we did for binary logistic regression? Would be e to the beta, right? Because there's only one beta. You don't have beta sub g. You can only, if you're talking about e, there's only one beta. So it looks like it should be, you remember what we had with polytomous, we had as many odds ratios as we had different categories. But now we're getting one odds ratio, okay? E to the beta, that's what this would be. Okay, so even though you've got several categories, you're getting one odds ratio, which is weird and a little different. So when you're doing ordinal logistic regression, you're not getting several odds ratios, you're getting one. What do you think that odds ratio is assuming? If you actually go back to for example, this picture, what is it assuming? It's just, you notice that these two odds ratios are the same? So it doesn't really matter how you cut the pie, how you divide the data into different subtables, you're still getting the same odds ratio. That's what it's sort of saying. So there's only one odds ratio. You're getting for any one coefficient. If you have other coefficients and you have an exposure variable that has more than two categories, then it's more complicated. It's not just an e to the beta formula. But that's what I'm saying here. So the odds ratio for the effective ACS status is just e to the beta here for this model. I mean, there's no subscript here, okay? Now, what does all this mean? Now, first of all, how do you do this? How do you do this? Now, this slide, if you're in your notes, there's some stuff in blue on this slide that's not in your notes, okay? Right? If you're looking at the slide. This stuff over here, the dash stuff, isn't in your notes. I added this about an hour ago, and I didn't want to put up a whole nother slideshow and have a whole thing. I'm sorry, I had to do all, what I did was I just added that table, this table, actually, did I add this table? I added this table. No, yeah, this is the hypothetical thing. I added that here. I just added it again. I just put it in here. It's the same thing to make it easy to look at what the code is doing. So this is the code for running the crude analysis. I've called it simple or crude analysis on the hypothetical data, which is table C. This is the code, okay? Now you notice I said input FRDE. What's FR stand for? It's the frequency of the numbers in these different parts of the table. Then it's got 30, 70, 120, 30, 25. That's these numbers. These different lines, 30, 71, that's this column. And then I put in that column. That's why I put this thing in here, so you could see what I didn't want to have to keep switching slides. Okay. So, and then what's the 2-0 mean? And what's the 1-0? And what's the 0-0? Well, you notice 2, 0. You see that's a 30? That's the 30? And you notice 1, 0? Well, that's the 70. So that's the code for the D and the E variables. I'm just putting in the data and I'm telling the computer how much, how many people I have in these different combine categories. That's all I've done to list this thing. This is one way you could describe the data. And then I say, run proc logistic descending, data equals, that's the name of the data set, simple, that's this data set, or that's what I called it, model D equal to E, so the outcome is the 0, 1, 2 variable, and that's the D variable, 0, 1, 2, and the E variable is the 0 or the 1 variable, and then I've got, why do I have FREQ FR? What's that doing? That's to make sure that when I run this thing, we know how many people there are in each of these cells. That's all I'm doing. And I say run, and then I'm running this model, okay? Now, you notice I don't have link equal G logit. I'm just running this model. Now, how does this will run the proportional odds model. Why isn't it doing binary logistic regression? Why is it doing proportional odds, not doing binary logistic regression? That's what I wanted to ask you here. Anybody figure that out? Because if you look at the D variable, in the data, how many values do you have for the D variable? 2 or 3? You have 3. So the computer is smart enough, I don't know, it's built into the computer to know that if you have more than 2 values for the D variable and you're doing this code, you're doing the proportional odds model, ordinal logistic regression, and not binary logistic regression. If I only had 0s and 1s on the D, then it would be doing binary logistic, and I don't need a G logit statement. With me so far? Again, still not heavy. It's still not that heavy. I don't think it's that heavy yet. Okay, so let's go on. Let's see where it gets heavy. Get heavy about the time we're ready to leave for the day, I guess. So I don't know. Okay, here's the output when I run this model. When I run this model, here's the output. Okay. I've got score test. You see the score test? 0.9281. This is for the hypothetical data. Score test is 0.9281, and the chi-score is This is just what I showed you before. 0.92 is 0.93. It's not significant. The score, and you get this in the output. I got model fit. I got -2 log L. I got analysis of the maximum, and I got odds ratio estimates. Now you notice. Look at the analysis of maximum likelihood estimates. I have intercept 2, intercept 1, and I have E. How many estimates for E do I have? 1. Why? Because go back to the model, go back to this model, it's not beta sub G, it's just a beta. So I'm only getting 1 estimate for the regression coefficient. That's all I'm getting, okay? And when I look at this 2.023, that's e to the 0.7044. That's what that is. 2.023 is when you exponentiate this coefficient. Okay. So what is that saying? And then there's the confidence interval around it. So what's that saying? What are we getting out of this? We're getting an odds ratio for the effect of exposure. Well, this is the hypothetical data set, but we're assuming the exposure is whether you're resistant or susceptible. We're getting an odds ratio of about 2. Okay. Now you notice that 2.023. Remember the 2 numbers I got where there was a 2 and a 2.06? Well, that's something in between. That's an average, right? If I go back to this table, the 2 and 2.06, and I'm winding these 2 numbers here, and I go back to this. 2.023 is in the middle somewhere. So what's the 2.023 doing? It's like it's taking those 2 tables and it's coming up with a summary score that you're getting from the 2 tables because the 2 tables are both saying that these 2 odds ratios are more or less estimating the same thing. And so the model is giving you some average of this. And there's only 1 odds ratio. So you're not getting an odds ratio compare high versus low or medium versus low. You're just getting 1 odds ratio. And you're saying the odds ratio is going to be the same because no matter how I cut the pie, so to speak, and no matter how I cut these different categories or ordinal categories, I just get the same odds ratio. That's what I get. Now, I haven't done anything with the other variables, so I'm going to have to do that. Now, here's again, this is the code that I'm now going to use when I deal with the real data, the data that I actually had. Okay. Now you notice proc logistic descending data equal to, now I'm using the main data. Okay. Now, and then it says class new X time. What's that doing? Dummy variables, right? So I'm putting this variable in the model. There it is in the model, but it's not a single categorical variable or continuous variable. It's a bunch of dummy variables because of the class statement. What else is in the model? The exposure variable and the two other variables that I wanted to control for. Is it an interaction model or a no interaction model? It's a no interaction because I haven't done any product terms. If I wanted to do product terms, I'd put in product terms of like this is E with Apache, E with Charleston, I could put in product terms and then do my modeling strategy if I wanted to do that. But I'm just trying to illustrate what's in here. So that's how you'd run this thing, okay? So what do you get? Well, let's look at what do you get before we do anything. Look at what do you get, because that may be a better thing to do. I'm skipping a bunch of things. Hey, oh, wait, ooh. Here's what you get when I run this model. This is page 29, slide 29 in your notes. I wanted to skip to it because I wanted to show you what you would get if you ran this model that has all the variables in it, okay? And it's a no interaction model, okay? Now you notice that, you remember there's the E variable, that's ACS status, there's Apache Charleston, and there's 7 dummy variables for 8 exposure times, right? That's what's in there, okay? So you notice that for every variable that's in the model other than the intercept, for every variable that's actually in the model, how many estimates are you getting for that variable? How many estimated parameters? How many estimates are you getting for the exposure variable? 1. Why? Because there's no subscript G. How many estimates are you getting for Apache? Well, there's no subscript G. For any of these variables, you're only getting 1 estimate. So that's what you're going to get if you run, but you notice there are 2 intercepts because you've got 2 intercepts in the model. Well, you're dealing with the ordinality by doing the intercepts, but you're getting a single estimate, and then if you exponentiate it, what you get is 1.987, and then you get these other things. So of all these numbers here, what's the number, given what the goal of the study was, what's the number of primary interest? The 1.987. Why? Assuming there's no interaction, that's the value that gives you the effect of the exposure variable controlling for the other variables in an ordinal logistic regression model that deals with these other variables. And it's, you see that it's almost a twofold effect. And but you notice that the confidence interval doesn't, the actual confidence interval includes the null value, so you can argue that it's not significant. So it looks like they got almost a twofold effect that wasn't significant. And this twofold effect is what you get when you actually consider all the different odds ratios you get if you cut the pie different ways, given the variables you're controlling for, and you average them all, you get about 1.987, but it's not significant. That's what you're getting. That's how the study works. Okay, and that's ordinal logistic regression. Okay, and so I'm going to go back now. I mean, that's the main thing. That's how you do ordinal logistic regression. But I got to do a little bit more on this thing, because one thing I haven't done is, what do you mean by the proportional odds assumption? Where did that come in? What's that? What's proportional odds? Okay, so we have to talk about that. And in order to talk about that, we have to talk about, well, what's the model look like? Okay, well, I'm going to just, well, first of all, this is slide 21. I've gone back. You know, I like to jump around sometimes when I think I'm trying to explain something better than if I just went linearly. Maybe I should have had it linear, but anyhow, look at slide 21. At the top of the slide, I've got the model, the general form. This is the general form of the proportional odds model. It's not 1 over 1 plus e to the minus. It doesn't have just one variable. It allows for several predictors in the model. And the predictors could even be product terms, even more general than that. But that's the form of the model. And you notice is probability that y is greater than or equal to g, And since there are G ordinal categories, there's G minus 1 alphas, and the alphas are ordered alpha 1 is greater than alpha 2, greater than alpha 3, and so on, whereas previously there were only 2, and alpha 1 was greater than alpha 2. So all the alphas, first one is larger than all the others. Okay, and for the proportional odds model for our study, this is what it looks like. This is what this formula boils down to if you put in what the variables are. It's got alpha sub G, and G there's only 3 categories, so G is 1 and 2. G goes from 1 to 2 because 3 categories means 3 ordinal categories means there's G minus 1 is 2. So there's only 2 alphas, and then act status is the first X. Apache's the second X, Charleston's the third X, and then they've got 7 dummy variables for the variable I've matched on, the exposure time. And that's the model I'm using. This is just a special case of this, and that's what I fit. So that's what, now, it's still not getting at what does all this Y greater than G mean exactly. It's not really, it's still a little complicated, and that's where I want to talk about just before I quit today. And I might have to repeat this thing next time because it's a little. Now what I've done on this slide, and I'm going to sort of skip it, but what I've done on this slide is to explain why when you use this model, why the alphas can be listed in this order. Alpha 1 is greater than alpha 2, greater than alpha 3, when this is the model, okay? And it's a little mathematical proof, and it comes from the fact that if you're talking about the probability, if G is 1, little g is 1, you're talking about the probability y is greater than 1, well, that's got to be greater than the probability y is greater than or equal to 2. There's more terms in this thing than there is in this term, and that's what I've written over here. And I've just gone through a little mathematical proof there, and then what I've wound up doing is going even further to show that if this was true, it turns out mathematically, the alphas have to be in the order that it is. In fact, on the next slide, I've gone through the details of why that's true. I've actually gone through that. You can do this for yourself if you want to do it for yourself. If you want to just accept it, this is why the alphas, but I've gone through the mathematics. If this is true, then this is true, then this is true, and therefore I'm starting with this, and I wound up that the one alpha is greater than the other. Big deal. Okay, but that's a proof. Okay, but this is the one I want you to look at. This is the one that sort of explains something. Now, you see at the bottom of this slide, there's a probability formula. Have you seen this formula before? And the answer is yes. That's what I've been showing you. Here's the probability formula. Here it is again. Okay? And there it is at the bottom of this slide. That's the probability formula. Probability y greater than g given x, that's the formula. That's what I'm showing it again. Okay? Now, there's another way. You remember when we were doing binary logistic regression, we talked about the logit formula? There's the binary formula, there was the P of x, and then there was the logit P of x. Well, there's a way you can come up with the logit formula even for this situation. Now, look at this. You have to look at this a little carefully. Logit formula means the log of something, right? It's the log. Remember, it was the log of the ratio. It was the log odds, right? Remember, it was the log odds, the log of P of x over 1 minus P of x? Isn't that what it was? P of x over 1 minus. Does this look like P of x over 1 minus P of x? Look what's here. Probability y greater than or equal to g, given x, divided by the probability that y is less than g. Is the denominator 1 minus the numerator? As somebody might say, you're darn tootin'. Or I don't know who would say that. But yes, the denominator is 1 minus the numerator. So this expression is an odds. And if you actually do the analysis, do the math, and you get the log odds, this is what you get for the model. The log odds is the linear part of the model. In fact, if the log odds is this, then the odds is this. The odds is just the one P over the other. And formula-wise, it's e to this, and if you take the log of it, it's just without the exponential. So that's what the logit formula looks like. Okay? So you can write the proportional odds model either this way or this way, or even this way. But these two ways, this is the way that maybe gets you confused. This is the way that makes a little sense because you're talking about a log odds. And the log odds is just a linear part in this model, just like it was when you're doing binary logistic regression. I don't know whether you're totally lost or whether you're just having the best time of your life here as I'm talking to you about this. But now let me show you, well, turns out that for SAS and Stata, they write the model differently. And we're not talking about Stata here, so I'm just talking on the SAS, so let's skip that. But now I want to talk about proportional odds. Okay, what's the proportional odds? Now, first of all, I just showed you on the two previous slides that the odds for subscript G is given. You notice there's only G, there's no subscript G. The J is the jth regression coefficient for the jth variable, but there's only one G here. That is, G changes depending upon which category you're talking about. But I'm just writing this formula on this slide again. This is the odds for y greater than or equal to G. That's the formula. Okay. And so the odds ratio is this odds for one person divided by this odds for another person. Remember when we talked about an odds ratio? We're comparing two different people. One person with one set of predictors with another person with another set of predictors. When we're talking about predictors, we're talking about the x's. One person called it x, we call it x star, and another person we call x. So the odds ratio would be this odds divided by that. And if we just replace what this says with this, look at this. Look at this, the math here. What's the difference between what's in the numerator here and what's in the denominator? What's the difference between what's in? The only thing that's different is that the numerator has person x star x's, and the denominator has person x x's. Isn't that right? But the alphas and the betas are the same because it's the same model. Okay. Now, when I do the algebra here, what cancels out? I'm doing the algebra. I'm taking e to the numerator divided by e to the denominator. What's going to cancel out? Well, I'm going to keep the e, but what's going to cancel out in terms of what's inside the brackets? Well, this is the same thing here as it is here, so that's going to cancel out. The alphas are going to cancel out, right? Alpha sub g cancels out. What do I get? I get e to the what? Now look at this formula. E to the sum, j goes from 1 to p, beta j x j star minus xj. Have you seen this formula before? And the answer is yes. That was exactly the same formula we had for binary logistic regression. Exactly the same formula. I mean, there's the only thing in the formula, we're talking about the difference between corresponding values of the predictive variables, and then we have the regression coefficient in there. But you notice this formula doesn't involve G. Why doesn't it involve G? Because we got rid of it because this is where G fits in when we take this ratio. So this formula doesn't involve the category that we're dealing with. So the odds ratio, comparing two different people, gives you an expression that only involves the differences between the x's and doesn't involve which category you're talking about. That's what this says. Okay? Now let's say it again in another way. So in other words, the odds ratio, all I did on the top of this slide is write what I was at the bottom of the previous slide, bottom of the previous slide. This is the bottom of the previous slide. Now I'm putting it at the top here. This is the odds ratio for comparing for category G or ordinal G, comparing two different people, but it doesn't have G in it. Okay? So that's saying the odds ratio doesn't depend upon the category, the ordinal category. You're only getting a single odds ratio. That's what it says. That's why you're getting a single odds ratio. But let's say it in another way. If this formula says that the odds, look, this ratio, y greater than g given x star over y greater than g given x is equal to this, can I multiply this ratio by the denominator? If this is true, isn't this true? This is simple algebra. If the numerator divided by the denominator is equal to this number, which doesn't depend upon g, then the numerator is equal to this number times the denominator. That's all. If a over b equals c, then a equals b times c. That's all I've done here. All I've done there. So if you think about what this means, this means that the odds for any one individual can be obtained from the odds for any other individual by multiplying it by some number. And that number doesn't depend upon g. So this odds and this odds, these two odds are in some sense proportional because they don't depend upon what category you're talking about. That's what we mean by proportional odds. Or we mean that the odds ratio doesn't depend upon g. That's two ways of saying the same thing. The odds ratio doesn't depend upon g, or any one odds can be obtained from any other odds by multiplying it by some number that doesn't depend upon g. So that's what we mean by the proportional odds assumption. That's all it is. And if it's satisfied, you can use the proportional odds model. So that's sort of what I've done here. And I think this is a good time to stop, okay? And it's a good time to stop because it's time to stop, okay? So that's the ordinal logistic regression, okay? And I'm going to review that at the beginning of class next time so you get a little bit more, experience with this thing. Hold it, Emily. And then we're going to talk about collinearity. So I'm going to still talk about this next time, okay? Yes?
How do you interpret that odds ratio?
Okay, again, it's the average of all the odds ratios you would get if you were able to cut the pie into all different ways you can cut the pie by keeping the ordering. That's what it means. It's a single overall odds ratio.
So would you say, if you were going to put it in your words, like the odds of having MDR bacterial is greater among people who have higher longer states? Is that how you put it?
The odds doesn't really depend upon whether you're dealing with high, low versus low, low. As long as it doesn't matter what way you break it up, you're getting a single overall odds ratio that says something about the overall effect of the exposure. You're not saying the odds for one group compared to a reference group and the odds for another group. You're not getting that. You're getting just one number. That's what you're getting. That's different. So what you get from polynomous is more than one number. What you get from ordinal is a single summary. Yeah. If you want more than one number, then you should do polynomous. But if you do polynomous, you're not taking advantage of the ordinal, ordinality.
Okay. Thank you.
Okay. Hold it a second. I gotta end this. I'm gonna stop this.